In this short demo, I'm going to showcase the Spark 2014 technology based on the code of the Tokeneer project. Tokeneer was commissioned by the NSA, the American Security Agency, to demonstrate the interest of developing systems with formal methods. Tokeneer is the software for restricting the access to a secure enclave to people with enough credentials based on their biometric information. It was developed in 2005 and open sourced in 2008. It was originally developed in Ada and Spark. The version I'm using here has been translated into the new Spark 2014 syntax with the help of a translation tool. I've opened the project in the GNAP Programming Studio development environment. In the Spark menu, you can see entries to examine files or to prove them, which correspond to the two analyses I will demonstrate. I'm going to request the analysis of this file, alarm. You can see that the tool issues a message saying nothing was analysed because I should first identify the parts that are in Spark. Indeed, my project is a mix of Ada and Spark code, and as a user I should tell the tool which parts are in Spark and can therefore be analysed. So let's switch to another file, admin token, which is marked as Spark code. Here the complete file is marked as such, but it could be individual subprograms in this file instead. This file contains many procedures and functions, but we are going to do the analysis of a single local procedure. I just have to right-click inside the procedure and select the Spark menu. Then examine subprogram. The analysis issues two messages about possible reads of a variable called verified, which may be uninitialized. By clicking on the magnify icon, I reveal the path in the program along which the variable is not initialized. Indeed, the variable verified is initialized by a call, which is not executed on this path. So the correct thing to do here is to initialize verified to a default value at creation. With this change, analysis does not find any more errors. Let's now switch to another file, admin, also marked as Spark code, and let's focus on function op is available in this unit, whose declaration and implementation you see on the screen. This function returns an operation corresponding to the name that was input by an operator, provided this operator has the right credentials for the operation. Otherwise, the function returns a null operation. I can ask to prove that this function does not contain potential runtime errors by right-clicking inside the procedure, selecting the Spark menu, then Prove Subprogram. The analysis issues one message about a potential access outside the bounds of an array. Looking at the type of index for this array, we see it should be an operator within admin privileges. And indeed, the function op is available should only be called with operators that have admin privileges. It happens that function is present provides this information, so we're going to add a precondition to function op is available, which requires that its parameter has admin privileges. With this precondition, there is no possible runtime error in the function. Now we can specify a security property on the function op is available, namely that when it returns a non-null operation, it corresponds to the name that was typed by the operator, and that the operator has sufficient credentials. This is the property expressed by the postcondition I've just added. Let's rerun the tool. The analysis issues a message that this property may not hold. By clicking on the magnify icon, I reveal the path in the program along which the property does not hold. Looking at the context of this path reveals that the test that guards the return statement is the opposite of what it should be. So, let's correct it and rerun the tool. The postcondition is now proved. This postcondition only expressed partially what the function does. We can go further and fully specify the behavior of the function in the postcondition. Here we say that when the function returns a null operation, then there is no operation whose name matches the input, and which would have been allowed for the operator. Let's rerun the tool. It returns a message saying that the property may not hold along the path that falls off the loop. Here the tool requires help from the user in the form of a special pragma called a loop invariant to summarize the known state after a number of loop iterations. Here is the needed loop invariant, which expresses that none of the operations seen so far in the loop match both the stated name and the operator credentials. Let's rerun the tool. No more messages, which means it proved that the function is correctly implementing the specified contract. To see what was proved, I can rerun with a switch to display checks proved. There are 10 of them, both runtime checks in code and contracts, and the satisfaction of contracts themselves. This ends this quick tour of Spark 2014. Visit www.spark-2014.org for more information.